Hi, my name is Vic, and today we're going to learn how to predict dog emotions from photos. We're going to start out by loading in a set of 15,000 dog images. Then we're going to train a deep learning model using PyTorch that can actually predict emotions from photos. And then we're going to evaluate the model and improve it. Let's dive in and get started. We'll build a neural network using PyTorch, and here you can see the network architecture. And by the end, we'll actually be able to pass in images of dogs and predict the emotion in the image. So this dog is happy, and we predicted that this dog was happy as well with our model. This dog is sad, and our prediction actually predicted that the dog was sad. So we have a data set of over 13,000 dog images that we use to train our model and make predictions. Let's dive in. What we're going to be doing is creating a deep learning model that can predict dog emotions from a photo of a dog. To make this simple, I created a data set and I shared the link. So you'll need to download that data set to actually be able to follow along. Please download that and just extract it in the same directory where you have Jupyter running. So we're going to use Jupyter Lab, as I mentioned. You can also use Google Colab or any form of Jupyter Notebook. A lot of IDEs have Jupyter Notebook now. And let's get started. There's a couple of constants that we need to specify. So we're going to specify the directory where our images are. And if you download the data that I shared earlier and you extract it, it'll create this directory called images. And then we're going to define our folders inside the directory. So we're going to use happy, sad, and relaxed. So these are actually the dog emotions that we're going to be trying to predict. And then I'm going to define my device. If you're not sure what I'm doing here, don't worry about it. This is basically a way to tell PyTorch, which is the deep learning library that we'll be using, how to actually make the predictions. I'm going to set it to MPS right now. If you have an NVIDIA GPU, you should set it to CUDA, C-U-D-A. If you don't have a GPU at all, you should use CPU. I'm setting it to MPS because I'm on an M1 MacBook, and MPS is the framework that Mac uses for deep learning. All right, now we're ready to actually start creating the model. So I'm going to import a few libraries. I'm going to import OS, which is a built-in library to Python, so you don't need to install anything. I'm going to import pandas as PD, so make sure you have pandas installed. Those are my two imports. All right, so we want to train a deep learning model. So in order to do that, we first need to load our data set and create labels for each dog image. So we're going to load about 15,000 dog images, and we're going to also load the labels, the emotions associated with each image. All right, so I'm going to create a list called img files. This will hold the path to each image file. I'm going to create a list called labels. So these will be the emotions. And I'll create a list called label code. So this is going to go from these text labels to an actual code like 0, 1, 2, because we need to actually predict a code. We can't predict a string. All right, now I'm going to loop through each of the folders, and each of the folders contains about 5,000 images, and the folder names are actually the emotions that are represented in the image. So let me actually show you what this looks like. So I'll open up the file browser here. I have a lot of files in this directory. Don't worry about them right now. The folder we want to look at is images. And we can see the emotions are represented as the folder names. So I can click into relaxed. And here I'm going to see a few different images. So I can open up an image. Some of these, the data quality from the image set I scraped is not always great, but here's an image of a relaxed dog. That dog does look pretty relaxed. So all of the images will look like that. All right, so we're going to loop through each folder. And what we're going to say is file name equals os.path.join image directory and folder. So what this does is it joins together the directory name, which is images, and the folder name, which is the emotion that we want. And then we're going to loop through each of the individual image files in that directory. So os.listDir will list the contents of a directory. So we're basically listing all of the images that we have for each emotion. And then we're going to say impath equals os.path.join fname im. So this is getting the full path to the image, including the folder names. Then we're going to add the name of this file to our image files. We're going to add the emotion to our labels. And then we're going to generate a label code. Okay. So what's this doing? So what this is doing is it's indexing the list folders, and it's finding the position of the emotion that we have for this given image. And then it's returning 0, 1, or 2, depending on the emotion. So it's converting from a emotion label, a string, to a integer. Okay, let's go back and actually run this code now. All right, so what this did is it created those 3 lists for us. So we can look at img files. It's going to be a long list of all of the images. Now we're going to use pandas to actually turn this into a data frame. Actually, I already imported pandas, so I don't need to do that again. We'll create a data frame called dataset, and that's going to use the pandas data frame constructor. And we are going to say our columns are going to be file name, which equals this image files list, label, which equals the labels list, and code, which equals the label code. All right. We can now check out our full data set as a pandas data frame. So we have 13,665 individual images. And for each image, we have the label. So the emotion that the dog in the image is showing, whether that's happy, relaxed, or sad. And we have the code for that as well. All right, now we're going to get into the deep learning. So we're going to import Torch, which is a Python framework for deep learning. PyTorch and TensorFlow are the 2 most popular. I like PyTorch because it's a little more flexible, in my opinion. People have their preferences. It's about half and half in terms of who uses which one. And then what we're going to do is we're going to set a random seed. So a lot of stuff that happens in deep learning creates randomness. And what setting a seed does is it makes sure that the random numbers are generated in a certain order. So that if you run the same code twice, you get the same result. So I'm going to go ahead and set that seed. All right, now here is where the device that we set earlier comes into play. So basically a device is a GPU or a CPU. It's what's going to be used to train the neural network. So what we can do is we can check to see if CUDA is available. If you have an NVIDIA graphics card, then you'll have something called CUDA, which is the most popular way to train machine learning models. It's the most popular backend. I actually have something called MPS because I'm using an M1 Mac. So I'm going to check if MPS is available. And that's true for me. Now, if both of these are false for you, you should use CPU as your device. If CUDA is available, you can use CUDA as your device. Or if MPS is available, you can use MPS. So I'm now going to initialize my Torch device. And for me, that's MPS. But be careful to set the correct one for you. All right. Now, the next thing we need to do is create a Torch dataset using our pandas data frame. The Torch dataset is going to be used to actually train our neural network. So from torchvision.io, we're going to import read image. And there's a full list of libraries you need to install in the README that I linked earlier. So you should see everything you need to install. Torch Vision is an extension to PyTorch that enables us to work with images. So computer vision, which is why it's called Torch Vision. And then from Torch Vision, we're also going to import transforms as T. And I'll explain what the transforms will do in just a little bit. And then from torch.utils.data, we're going to import dataset. And then a final import, we're going to import a Python standard library called math, which just comes with Python. Okay, so in Torch, datasets are defined as classes, and a dataset tells Torch how to read in your data. So we need to define a class called dog dataset, and it's going to extend the base torch dataset class. So if you're not familiar with classes, are basically a way to organize your code more effectively. I'm not going to go into a lot of depth about what classes are and how to use them, but this class is going to have several methods in it that do various things that are necessary for Torch to read the dataset. So we're going to define an initialization method. So this method will take in a parameter called dataset, which will be our pandas data frame that we created earlier. We'll assign that to a class variable called dataset. Then we'll define something called augments. So we have 13,000 images. Many deep learning models work with millions of images to get good accuracy. So what we're going to do is we're going to create new images using our existing images. And we're going to use these Torch Vision transforms to do that. So one transform we're going to use is called random horizontal flip. And I'm going to set the probability of the flip to 1. So what this means is it's going to take every image and flip it horizontally. So the right side becomes the left side and the left side becomes the right side. So that basically creates a new image as far as our deep learning algorithm is concerned. And it helps us essentially add more images to our data set without going out and scraping more images. Then we're going to do random rotation, and we're going to say 90. So that will randomly rotate the image between 0 and 90 degrees and create a second image. And our last augmentation will be called auto augment. So auto augment is a PyTorch class that basically applies a set of predefined augmentations to automatically create a new image. So basically, for every image in our dataset, we're going to create 3 additional images using augmentations. All right, then we're going to define something called a normalizer, and we're going to use a transform called compose. And what compose does is it applies multiple transformations in order. So the first transform we're going to apply is convert image dtype to torch.float. So by default, our image is going to be read in. So each of those dog images I showed you earlier will be read in, and they will use integers to represent each intensity value in the image. I'm not going to explain exactly how image data is stored and like how all of that works, but at a really high level, images are stored as a set of integers. So each integer represents a pixel and a pixel intensity value from 0 to 255. So if you think of an image, it's actually just stored as a matrix of integers. So what we're telling PyTorch is to convert those integers to floats, because we need that to actually normalize the image. And what normalize does is it standardizes the image intensities and standard deviations of the dataset, which just makes training a little bit faster. Where did these weird numbers come from? These are the numbers used to normalize against a very popular dataset called ImageNet. So I just copied the same numbers from them. All right, so normalization basically just standardizes all the image intensities into a range and just makes it easier to train a deep learning model, easier and faster. All right, now we need to define a method called len or length. So when you call this class and ask for its length, this function will return the number of items in your dataset. So what we're going to do is we're going to return self.dataset.shape0, which is going to return the number of rows in our pandas data frame. But we're also adding in these augmentations. So we're going to multiply it by the length of the augments plus 1. So we have 3 augmentations here, which actually means that our data set will be 4 times as large as our original data set, because we have our original images plus each of our images with this augmentation applied, which means we essentially have 4 images for every original image in our data set. So that will return the length of our original data set and all of the augmentations. Then we're going to define a method called classes. So what this is going to do is return the number of items that we're trying to predict. So we have 3 different labels that we're trying to predict: happy, sad, and relaxed. And this class's method will just return the number of unique labels. All right, now the most important method we have to define is called getItem. So basically, Torch is going to call the length function, and it says, okay, we have this many items in the data set. Then it'll iterate across the data set and get each item individually. So it'll pass in an index like 0, 1, 2, 3, 4, just like you index a list, and it'll expect to get an element in the data set back. So in here, we need to basically read in our image files and handle any augmentation we want to do. Okay, so we know that we need to pass back an augmentation if the index that we get is higher than the original number of rows we had. So we had 13,000 rows, but we're multiplying that by 4 because we're adding in 3 augmentations for each image. So what we're going to say is if the index we get is greater than the length of the data set, then we know that we need to return an augmentation. So if this value is 0, then we don't actually augment the data. If it's a 1, we apply the first augmentation. If it's a 2, we apply the second, and so on. And then we just modify our index by taking a modulus. This ensures that our index is within the range of our original number of rows. So if the index is 26,000, it will basically, a modulus will adjust that number so it's between 0 and 13,664. All right. Now we're going to grab the row from our data set that corresponds to the image that we want to return. All right. So basically, we're grabbing one of these rows based on the index that's passed in. Then we're going to actually read our image in. So our file name is the actual path to the image. And then we're going to use the read image function provided by Torch Vision to actually read that image in. And then we know the label is just the code from that same row. And then we'll say if augment is greater than 0, we're going to apply an augmentation. So what we're going to say is image equals self.augments, augment -1. So this -1 is happening because this augment value will start with the number 1. But we want to index our augments list starting with the index 0. So that's why we subtract 1. And then we'll call the forward method of that augment. And what this is going to do is it's going to call one of these augments. So random horizontal flip, random rotation. And then it's going to call the forward method. And what the forward method does is take in an image and return the transformed version of that image. So it'll apply the horizontal flip, it'll apply the rotation, etc. All right, and now we just need to normalize our image. And we can return the image, the label of the image, and the path to the image. So we'll return 3 values. All right, so that's our dog data set. So I'll go ahead and run that to just define everything in it. And we can actually call this class once it's defined to initialize it. So we're initializing an instance of this class and assigning it to the variable data. All right, so now that we have our data set, we need to split this up into training and test data. So training data is what we're going to use to train our model, and test data is what we're going to use to evaluate our model. So we're going to define the size of our train set and our test set. So that's the size of our training set. It's going to be 80% of our data. And then our test size is basically going to be the other 20% of our data. And then we can go ahead and split our data up. Basically, what we're calling is a function called random split, which will randomly split our data up into a train and test set based on our train size and our test size. And we're going to pass in a generator. And the reason we're going to pass in a generator is this split is random, but I actually want the split to be consistent every time I run it. So we're going to call manual seed, and we're going to pass in a random seed of 1. And what that means is every time I run this random split, it will happen in the same order, and the same values will be assigned to the train and the test set. Okay, so let me run that. And then we're going to see train data is now a torch subset of our original data. It took 80% of the rows and assigned them to the train data. Okay, now we need to create something called a data loader. So we've defined our data. A data loader will help load the data in as we train our deep learning model. So it'll create batches and it'll be able to be called by our training methods. Okay, so we're going to define batch size. I'm going to set this to 64. So this is the number of images that we want to use to train the deep learning model at one time. So the less memory you have for your device, your GPU or your CPU, the lower you want batch size. You also don't want to set batch size too high, because if you set it too high, your results can become unstable. So I like 64. You can definitely experiment with this. And then I'm going to set a parameter called epochs. So this is the number of times you want to train the model. So we have our whole data set of 13,665 times 4 rows. So it's basically how many times you want to feed all of those images into the neural network. And each time the neural network sees the images, the better it gets at making predictions. So generally you want to set epochs pretty high, but you don't want to set it so high that your algorithm is just, it's already converged and it's hit its maximum accuracy and it's still running. So you can definitely experiment with this value. Okay, now we're going to create data loaders that define how to load our data. We're going to create a training data set by passing in our training data. We're going to specify batch size. And we're going to say shuffle equals true, which means shuffle around the order of the data. And then we're going to create a data loader for our test data also. All right. Okay. So that is all of the pre-processing and data. I promise the next step is actually training the neural network, and I am going to go ahead and do that. So we're going to create another class for our neural network, and this class will actually have all of the code for our neural network inside of it. So from Torch, we're going to import NN, which is just the neural network module in Torch, and we're going to define a class, which I have cleverly named neural network, but you can name it anything you want. And it's going to extend a neural network module from PyTorch. So we're going to create an initialization method, just like we did for the dataset. And it's going to take in the number of classes to predict as a parameter. And we're going to make a call to the superclass. So if you're familiar with classes, this n.module is a class definition that we're extending. This is just calling the definition of the init module the init method in this nn.module class before we do our own custom initialization. Okay, now we're actually going to create the layers of our neural network. And one layer that we're going to use extensively is a batch normalization layer. So what this does is it normalizes values in a batch to get them into a certain mean and standard deviation. This is a way to prevent overfitting. It can also make training faster and more stable. Okay, now we're going to define our full network. So we're going to call this neural network.sequential class. And what this does is it takes a set or a list of different neural network layers. So starting with the first layer, second layer, third layer, and it runs them all in order. So we're going to build up our neural network layer by layer inside this sequential container. All right, so our first layer is going to be a convolutional neural network that is going to take all 3 input image channels, red, green, and blue, and it's going to turn them into 64 channels, where the neural network is basically looking at all the channels and creating new channels based on those. And what this lets it do is identify higher level features like the ear of a dog or the teeth or the nose. So that's essentially what a convolutional neural network does. It looks at several image pixels together and creates a higher level feature from those pixels. And we're going to look at a 4x4 chunk of the image, and stride is going to be 2. So stride defines how many pixels the window is going to move. So we'll look at a 4x4 slice, then move over 2 pixels, look at another 4x4 slice, move over 2 pixels, and so on. All right. I wish these are pretty short, so I can't like show you diagrams and explain how all of the neural network ties together. But basically, a convolutional neural network is a way to look at an image and pull out higher level features and structure from that image. All right. Then we are going to normalize after this layer. We're going to call ReLU, which is an activation function. And then we're going to max pool. And what this does is it shrinks the dimensionality of each of our individual channels. So we now have 64 channels. We're shrinking the dimensionality using max pooling, which just makes the algorithm a little bit more stable and resistant to overfitting. All right, now we'll create another convolutional layer. And this neural network is based on the ResNext architecture, at least the first few layers, because that neural network has 100 or more layers. It's based on the first few layers of the ResNext architecture, which is a very popular architecture for image recognition. All right, so we call another convolutional layer. And we already have 64 channels essentially in our image. So this just goes from 64 to 64, and it's using a kernel size of 2. So we're looking at 2 by 2 pixels, 2 pixels by 2 pixels, and creating higher level features from that. Then we call batch normalize again. And then we will call a very similar layer again to basically continue generating higher level features. We'll batch normalize again after that. We'll call our activation function, and then we will call max pooling again. All right, so that is the full part of our convolutional neural network, our sparse part of our neural network. And each layer will basically pass information to the next layer. And some of these layers are layers that are designed to generate features, and other layers are layers that are designed to either prevent overfitting and improve training speed and accuracy, like the batch normalization and the max pool, or activation layers, which go from kind of the floats that are in the convolutional neural network. They pass them through a simple activation function to put the values into a certain range. All right. Now, after the sparse part of our neural network, we need a dense part of the network. And the dense part of our network basically goes from this part, which has essentially generated features from our image. So this part has basically looked at different parts of our image and said, okay, these are parts of the dog that indicate certain emotions. And we're going from that to actual predictions. And to do that, we're going to use what's called a dense neural network, which basically means that every input in one layer is connected to an output in the next layer. And we're again going to apply these sequentially. So the first linear layer that we apply is basically going to take all of the features from the previous layer and convert it down to 64 features. And then we'll go from those 64 features to our actual predictions. So just our number of classes that we actually have. Okay, so that's all the initialization. Now we create a forward method, which actually runs our neural network in order. Okay, so first we apply our convolutional layers to the input. So the input is going to be an image, or a batch of images rather, 64 images. We're going to apply our convolutional network to that batch. Then what we'll do is we will flatten our layers. So when you're thinking about it, an image is really a matrix, right? In our case, 384 pixels by 384 pixels. And it's considered two-dimensional. right? There's one dimension going across, one dimension going down, rows and columns. What flatten does is it turns that into one single list, one really long vector. And we need that for the dense layers to actually work. So we flatten out our matrices into just one really long list of numbers. And then we pass this into our dense layers to actually get a prediction. And what we end up with is for each of our classes, we end up with a single number that indicates whether our image is part of that class. So whether the dog is sad, happy, relaxed. Okay, and then we return our predictions. Actually, these aren't probabilities, but they are numbers that indicate which class the image is in. Now we're just going to create a quick list of labels. So this will just show us our individual labels that we'll get out of our model. Then what we're going to do is define our model. We'll pass in our labels so the neural network knows how many class predictions to output. And then we are going to send it to our device, CPU, MPS, CUDA, whatever your device is. This model will get sent to your device for training. So here I typed max pool instead of max pool 2D. So I had a little typo there, which is why I got an error. Okay, so now we can take a look at our model. So we can see that Torch has defined all of our layers. And we can see those as part of the model. Okay, now to actually train our neural network, we need a loss function. So a loss function is basically what we're going to try to optimize as we train our neural network. So we're looking at cross entropy loss, which is a common way to get loss for a classification task. So basically what this is going to say is we want to predict the correct label for each image, and it's going to penalize our algorithm if we predict the wrong label. Then we need an optimizer. So the optimizer is what's going to optimize the weights of our neural network against this loss function. And we're going to use something called stochastic gradient descent, which is a very common optimizer. This and Atom are the two most common. And what you pass into this are the parameters from our model and a learning rate. So the lower the learning rate, the slower the model will improve accuracy. But if you set a learning rate too high, just due to the way gradient descent works, sometimes the model won't get any better either. So you need a learning rate that's just right, not too low or not too high. And that's true for a lot of parameters in neural networks. You need a value that's just right. And if you set it too high or too low, things will not go as well. So 0.001 is one that seems to have worked well for me, but you can definitely play around with the learning rate. All right. Now we're just going to define a variable called size, which is just the length of our training data set. And we're actually going to write the loop that trains our deep learning model. Finally, so we're going to say for epoch in range epochs. So we're going to repeat this code once for every epoch. And we're going to iterate through batch, then images, labels, IMG paths, in enumerate, train. Okay, so what this is going to do is loop through our train data loader. Our images have been batched together in batches of 64 images at once, and it's going to pull each batch out one by one. Okay, we're going to call this zero grad method to tell the optimizer that we're starting a new batch. We're going to send the images to our device. We want our neural network and the image data to be on the same device. Then we're going to get our predictions. So we're going to pass our images into our model to get our predictions. Oops. I hit run too early there. Then what we'll do is we'll grab our labels. So we're going to send our labels to our device. And then we will predict our loss. So the loss function takes in our predictions and our actual labels and compares them to come up with a number that indicates how good or bad our model was. All right. Okay. Then, given our loss, we're essentially going to propagate that backwards through our neural network, and we're going to have the optimizer try again to improve our weights to improve our loss metric. All right. And then for every epoch, we are going to essentially print out a couple of items. So we're going to grab the current loss value, and we're just going to print it out. Okay. All right. So what this is doing is it's basically each epoch, it's looping through all of our data by batch, feeding it into our model and training our model. Then when each epoch ends, we're finding the current loss value, and then we are printing it out. So we're printing out the current loss of the model and what epoch it's on. All right. Let me just reinitialize some of these because I hit run too early. All right. Now we can actually run this model to train our deep learning model. So we can run this loop to train our deep learning model. All right. So this is going to take a long time. It's actually not going to finish today. So I actually created a pre-trained model that I'm going to load just to show you what it looks like. I ran this overnight. If you have an NVIDIA GPU, it'll run a lot faster, but it runs a lot slower on CPU or MPS. All right. Ignore this line of code if you don't want to use a pre-trained model. I shared a link to the pre-trained model. You can download this if you want to. But I can go ahead and load the model. And then what we can do with the model is we can make predictions against our training set. All right. So we're going to create lists to hold our predictions, our labels, and our image paths. And then we're going to say with torch.nograd. And what this means is it's telling PyTorch that we're actually in inference mode. So we're making predictions on a test set. We're not actually training the model. We're again going to loop through. This time we're going to loop through our test data. And what am I typing? Enumerate test. So we're going to do something very similar to what we did before in our previous loop, except this time we're not going to train the model. We're just going to get the predictions. Okay, so we pass our images into the model to get predictions. All right. And then we call torch.max. And what this does is for each image, it gives us the class that was most highly predicted. Okay. Okay, so then we're going to take the actual labels, the predicted labels, and the paths to the actual images and append them to these lists. All right, so I can go ahead and run that. Okay, then we're going to import numpy as np, and we can actually turn these into numpy arrays. This is basically taking our predictions, getting them off of our device to our CPU, and then converting them into numpy arrays from PyTorch tensors. Okay, so that's how we extract our predictions. And then for our labels and our image paths, it's very similar. We just replace this, and then paths doesn't need, paths never went to the device, so they don't need the fancy we can just do a more simple list comprehension there. All right, so now we can get our exact match accuracy by looking at creds equals labels dot sum. So this finds the number of times when our prediction matched our label, and then we divide it by the length of the labels to get a percentage. So I would run that. This may take a little too long even for inference than we have, but this was about 57% when I ran it before, and that's pretty good. Okay, and once we have our predicted accuracy across the whole data set, we can then move on to actually figuring out the accuracy for each class. So we'll first create a data frame. So we'll create a pandas data frame. And we'll have a column for the predictions, a column for the labels, and a column for the image path. And we're actually going to use that to display the image later on. Then what we'll do is we'll create a column called correct, which is just going to tell us if our prediction for that row was correct. So we'll just check if the prediction equals the label. All right. Now what we can do is we can actually create the actual label of our prediction. So here the prediction is a code 0, 1, 2, but we can actually convert that to a label. So to do that, we just have to map from the code back to the text label. So to do that, we go back to our folders list and we just index that list based on our code. So that gives us our predictions column. Actually, I'll just call that prediction, not predictions. And then we'll create an actual column where I'll just copy and paste this. It's mostly the same code, but I'll rename this to actual, and this is going to be label. So I'll run that. Now what we can do is we can say the predictions data frame, we'll group it by our prediction column, and then we'll apply a function to actually summarize the percentage correct for each label. So this is just finding the total number that we had correct and dividing it by the total number of predictions we made for each of our different classes. So you can see our model is pretty good at predicting if a dog is sad or happy, not as good at predicting if the dog is relaxed. All right, now what we can do is we can go ahead and display actually a little part of this data frame so we can actually visually see what our model is misclassifying. So let's go ahead and create a data frame called disp for display. This is just the first 25 rows of our predictions data frame. And then we can actually show the image using a pandas image formatter. So we're going to return, I'll use single quotes outside. So we'll return some HTML, which pandas is then going to display for us if we tell it to. So what we're doing here is we are saying to style our data frame using this function. So for the path column, we're actually going to pass each of our paths into this function, which will render an HTML image tag, which will show up in Jupyter Notebook. So here we have it. So you can see the first 25 rows of our predictions. You can see the actual value, if the dog, what emotion the dog was, and we can see our prediction. So our prediction for the dog's emotion. And for these first two, we were correct. So this dog is sad. We predicted it would be sad. For this dog, we are actually incorrect. We predicted that this dog was relaxed, but it's actually sad. This dog is relaxed, and our prediction was correct. So by going through each of these and just seeing what we misclassified or didn't, we can start to see patterns that can hopefully help us improve the algorithm. And if we want to improve this algorithm, there's a few things we can do. So the first and by far the best thing we can do is get more images. So in a previous video, I showed how we can actually build an image dataset. So if you scrape more images using that technique, you'll improve your prediction accuracy. Another one is to actually augment the dataset with more augmentations. You can also try increasing the number of epochs in your training. You can also change the network architecture. So you can try using a more complex, deeper network to get better accuracy. But by far, your biggest accuracy gains will be from just getting more data. You can also try changing the learning rate, which is another parameter you can try to optimize. Okay, so I hope that's a good look at how to build a model to predict dog emotions and how to keep improving that model.